Welcome to Asteroid Day Live 2021. I'm Lisa Burke, back with another fascinating look at the cutting edge of asteroid research and planetary defence. It's been an extraordinary year of progress and achievement for asteroid science, and over the next 5 hours we're going to bring you fully up to date. Now, this year we have a very special theme. On February 17th, 2021, we observed the 25th launch anniversary of the first dedicated mission to an asteroid, NEAR-Shoemaker. In today's programme, we will reflect on this mission and its legacy. Before we start, we want to say a big thank you to our sponsors who make Asteroid Day Live possible. Broadcasting Centre Europe, whose studio I'm currently in. SES, who is broadcasting the Asteroid Day signal to their satellites in the Middle East and Europe. The B612 Foundation, the Luxembourg Chamber of Commerce and the Luxembourg Space Agency. And we also want to thank this year's partners, the Association of Space Explorers, the Planetary Society and the European Space Agency, without whom we could not deliver such a rich and interesting programme. And a special mention goes to Twitch TV for carrying this stream to a global audience. Hello to anyone watching right now on Twitch. For this year's programme, we will begin with a look into how experts find and track asteroids. Following that, we will hear about scientifically investigating them, defending our planet against asteroids, and how they will help us further explore the solar system. So let's dive into the fascinating world of asteroids. In 2020, the International Astronomical Union's Minor Planet Centre catalogued its 1 millionth asteroid, and this dizzying number of discoveries is set to explode in the coming years as new search facilities come online. From amateur astronomers to near-Earth object neodynamicists, today, finding and tracking asteroids isn't just reserved to universities and space agencies. To start us off, astronaut Leland Melvin is here to answer the most fundamental question: what exactly is an asteroid?
An asteroid, they're actually leftover rocks from the formation of our solar system 4.5 billion years ago. The largest one is Sirius at 946 kilometers in diameter. That's really, really big. And the smallest are just about a meter wide. So, and there are millions and millions of these things floating around. So it's really important that we understand the different types, from rocky to carbonaceous to even metallic. And they provide an endless, now check this out, an endless resource for research and exploration milestones. So it's a pretty cool study, and many people can do this. Anyone can do this. You just have to be curious and be able to look up and just find out what's out there.
In astronomy, an asteroid, a comet and a meteorite sound like three different things, but actually they're interrelated. Let's start with asteroids. Asteroids are small rocky bodies, much smaller than planets, orbiting the sun, just as the planets do. They range in size from perhaps a meter across, something you can almost put your arms around, up to over 900 kilometers across for the largest asteroid Ceres. In fact, Ceres is so large, we also call it a dwarf planet. Now, an interesting thing about asteroids is that they're primarily composed of rock, but it's not solid rock for most of those asteroids. Any asteroid that's about 10 kilometers across or smaller, we actually think are rubble piles, i.e. they're kind of conglomerations of smaller bits of asteroid, all stuck together by self-gravity and weak binding forces, what we actually quite often call sticking forces in physics. Now, those are the rocky asteroids. Comets, on the other hand, have a lot of ice in them. So that makes them actually quite fragile compared to asteroids. In fact, comets have a density about half that of an ice cube on average, even though they have a lot of water ice in them. It's very porous. Now, the difference between an asteroid and a comet when you look at it through a telescope depends on where you see it. If you're looking at a comet when it's near the sun's heat vaporizes the ices on the surface, producing an atmosphere, and the tails of a comet from the expelled gases, plus any small bits of rock or dirt that was also once in that surface of the comet. So telescopically, comets and asteroids can look very different, but they're both small objects orbiting the sun. Now, the reason that we're here for Asteroid Day is that some of those asteroids and some of those comets can have orbits around the sun that bring them close to our planet, and they can fall onto the Earth and hit us. If a piece of asteroid or comet makes it through our atmosphere and lands on the ground, we call that remnant, that small piece that survived, a meteorite. And in fact, this rock that I was using a little earlier is indeed a meteorite. It's a piece of asteroid that made it through the Earth's atmosphere, in this particular case a few hundred years ago, to be found lying on the ground. The interesting thing is that the vast majority of meteorites that we have found on Earth come from asteroids. Some rare examples come from the Moon and even the planet Mars, but we have never found a meteorite that definitely came from a comet, and that may be because they're very fragile. But we would love to do so because we know when we study meteorites from asteroids that they allow us scientifically to decipher the history and the evolution of our solar system when we put it together with studies by telescopes. So those are the differences between meteorites, their parent asteroids, and the icy comets.
This year is the 25th anniversary of the launch of NASA's NEAR-Shoemaker space mission, the first dedicated mission to an asteroid. And in the last quarter of a century, we've seen a string of other missions to asteroids, and there's no sign of that interest drying up, as there's at least 5 new missions planned in the next 3 years. These days, images and data about asteroids is everywhere, but that wasn't always the case. The first close-up images of asteroids were taken in 1991 and 1993 during the Galileo mission's journey through the asteroid belt to reach its destination of Jupiter. And these images fueled scientists with myriad questions about asteroid orbits, the compositions, their interior structures, and their role in the formation of our solar system. In 1996, NASA launched its first ever dedicated asteroid mission, NEAR-Shoemaker. NEAR would visit 2 asteroids, Matilda and Eros, providing us with a treasure trove of information. And today, I'm joined by a man who's not only seen the span of that asteroid research take place, but he's been instrumental in making it happen. In 1997, Andrew Cheng was a project scientist for the NEAR-Shoemaker mission, and today he's the chief scientist for planetary defense at the Johns Hopkins University Applied Physics Laboratory. and the lead investigator for the Double Asteroid Redirection Test, or DART mission. Andy, thanks for joining us.
Pleasure to be here.
Now, back when you were launching NEAR in 1996,
As a young man,
what did
yes.
we, long time ago, yeah, what did we know about the sort of the asteroids then, and specifically their orbits, and how did you choose your targets?
Well, Eros was chosen because it was one of the largest near-Earth asteroids, known as the second largest at the time. It comes close to Earth, and it was just supremely interesting for both of those reasons. And as you said, we were just tantalized by the glimpses of, these were main belt asteroids, Gaspar and Ida, that were seen by Galileo. And we didn't know if the near-Earth asteroids would look the same. We had no idea what we would find when we actually got up close and studied them for the first time.
What did we think about the differences in the orbits and how they had got into sort of their near-Earth asteroid orbits and come from the belt? What did we know about it then?
Okay, at the time, in fact, one of the major forces that causes main belt asteroids to leave the main belt and eventually come in close to the near-Earth region to become near-Earth asteroids. One of the two main reasons why that happens was not even fully appreciated, was not understood at all at the time. So that was the more recent advance in our understanding, and that is the Yarkovsky force, or it's the force of, it's a radiation caused by the uneven heating of the asteroid's surface by the sun, and the re-radiation of this energy back into the space is also uneven, and that causes the asteroid orbits to change. So that's one of the reasons why asteroids go into the near-Earth region. The other one is a complicated set of, it's the many body interactions with the major planets causing what we call secular perturbations of the orbit, and that also causes asteroids to drift out of the main belt and into the near-Earth region. But asteroids, as you say, in the near-Earth region don't stay there very long. They only live as near-Earth asteroids for tens of millions of years. And they fall into the sun, or they're ejected from the solar system out past Jupiter, or they hit the Earth. So we don't like the latter, of course.
We don't want that to happen. No,
Right.
Absolutely not. It's quite amazing, isn't it, how dynamic the asteroids are, really, and in their movements. When you launched NEAR, were any of its investigations geared towards trying to understand some of that, or did that come out of your data, for example?
We were trying to understand, yes, NEAR was about trying to understand how the asteroids were put together and also what they were made of. So we had measurements of the composition, and we had many studies of what the surface looked like and how its interior was put together. So measuring the density, measuring the gravity fields, measuring chemical, elemental, and mineralogical composition of the body.
It's absolutely a fascinating mission. So thank you so much, Andy, for telling us about this initial look at NEAR-Shoemaker. We're going to keep coming back to you throughout the Asteroid Day live broadcast to get updates about how NEAR contributed to all the many facets of asteroid science that we talk about today. But for the moment, Andy, thank you very much.
Thank you.
My interest in astronomy started in 1997. I remember perfectly that night because I was imagining a galaxy in the Lion constellation, and there was a point of light moving over the time, and of course it was an asteroid. At the beginning it was like a problem in the image because it was a trail I really don't wanted, but I understood that an asteroid can teach a lot of things, and I started just learning more about them, and it was love at first sight, to the point that I decided to study this topic quite a lot. And as an astrophysicist, asteroids are now my main field of interest. So everything started on that night many years ago, and I'm happy with asteroids every time. I think that everyone should try to look up for asteroids. I understand that you need a telescope, sometimes powerful telescopes, but sometimes we are lucky and a bright object really shows up in the sky and you can observe it with a binocular, for example. Or you can contact people around you having telescopes and they can help you just setting up for this experience. I think that looking up, looking for an asteroid, enjoying its motion, understanding that that little point of light is bringing some very special about the history of our solar system will make your experience to look for it and observe it really unforgettable. This is my experience, at least. I must say that for me, staying outside under the stars at night is one of the greatest experiences I can actually have. I've been doing this since my childhood. At the time, the sky was much better because in these few decades, light pollution made it almost impossible to see the same stars from the same places where I grew up. And every time I can, I still try to go outside to look up and enjoy the real sky. Even if I have created the fully robotic facility of the Virtual Telescope project, I still believe that it is much better to experience the sky by yourself. And my decision to start the Virtual Telescope project was for personal reasons, because I live in Rome. The observatory is about 100 kilometers south. And for observing, I had to travel quite a lot, and it was not easy. This is why I decided to approach this thing in a different way. That is, making the access remote. And it was a great choice. And now the Virtual Telescope is truly productive, and I have fun even when I connect remotely. But still, I prefer to be out there under the stars.
Asteroid Matilda orbits the Sun in the main asteroid belts between Mars and Jupiter. It's a medium-sized asteroid, just over 50 kilometers or 30 miles wide. NASA's NEAR-Shoemaker mission visited Matilda in 1997 as the spacecraft flew by on its way to meet with its primary target, asteroid Eros. Although the flyby was brief, NEAR-Shoemaker learned a lot about the asteroid. When the spacecraft flew by, Matilda's gravity pulled it slightly off course. Scientists used this deflection to calculate the mass of the asteroid. NEAR-Shoemaker also captured more than 500 images of the asteroid, which scientists used to calculate Matilda's volume. Combining these two measurements to find Matilda's density, scientists learned that instead of being a single slab of rocky material, the asteroid is actually a loosely packed conglomeration of fragments. Astronomers began to call these kinds of asteroids rubble piles. NEAR-Shoemaker also saw that Matilda is pockmarked with huge impact basins, including one that is 20 kilometers or 12 miles long, which stretches halfway across the asteroid. The battered appearance of Matilda speaks to the fact that many, perhaps most asteroids, are not unaltered remnants from the early solar system. Instead, they've lived turbulent existences in which collisions are frequent, leaving these space rocks battered and scarred.
The Asteroid Day 100X Declaration. It's a call for humanity to raise the awareness about discovering the asteroids and to ask to discover 100 times more asteroids per year. Now we discover about 1,000 new dangerous asteroids every year. This is a very small percentage of the very dangerous asteroids that fly around the sun and could hit the Earth. Discovering 100 times more asteroids favorises not only our knowledge in knowing what they represent for the Earth and how they could impact the Earth, but in the same time to prepare the world for impact or to build means to deflect their orbit. Rising the awareness and rising the level of discovery of the asteroids, it's very important to protect us in the future.
So where do we find asteroids? Well, we're generally familiar with where the planets are in their orbits about the Sun. We have the inner planets going from Mercury out to Mars. Earth is the third planet from the Sun. And then there's a big jump until we get to the first gas giant planet, Jupiter. Well, most of the asteroids we find in the solar system orbit between the planets Mars and Jupiter. And if we count the distance between the Sun and the Earth as one unit of distance, which we call an astronomical unit, then the asteroid belt lies between 2 astronomical units and roughly 3.5 astronomical units from the Sun. So that's roughly 2 times to 3.5 times further from the Sun than the Earth is. And in this asteroid belt, we measured about 1 million asteroids that are larger than 1 kilometer across. And they are all out there orbiting the Sun in their own orbits. In fact, there are some asteroids a little bit further out actually sharing the orbit of the planet Jupiter. We call these the Trojan Asteroids, and they have particular scientific interest because we think there may be a lot of ice in those asteroids, similar to comets. Now, of course, the reason for Asteroid Day is that not all the asteroids are out there in the asteroid belt. Some are much closer to us. Some have orbits within the inner edge of the asteroid belt, first of all crossing the orbit of Mars, and we call these Mars crossers or Mars crossing asteroids. And then even closer to the Sun, we have asteroids that cross the orbits of Earth and Venus and even Mercury. And these are the near-Earth asteroids. In fact, for every 1,000 asteroids in the asteroid belt, there's generally about 1 asteroid near the Earth. But that still means that they can hit us from time to time, and of course that's what we're all interested in.
Hi, my name is Ed Liu, and I'm the Executive Director of the B612 Asteroid Institute, a co-founder of the B612 Foundation and a former NASA astronaut. Welcome to 2021 Asteroid Day Live. B612 is an organization dedicated to protecting the Earth from asteroid impacts through scientific research, technology, and public education. As the first and earliest founding partner of Asteroid Day, B612 is pleased to continue this support. B612 was founded in 2002 by myself and a group of other planetary scientists and astronauts with a vision to develop the technology to track asteroids and deflect them if needed. Since then, B612 has grown into a world-renowned organization and scientific institute with a key role in the field of planetary defense. For years, B612, our partners, and a global community of donors, dedicated scientists and researchers have advocated for increased asteroid detection capabilities. Asteroid detection is now discussed seriously in scientific, governmental, and public conversations. B612's Asteroid Institute continues to advance the science and technologies to discover, track, and calculate the trajectories of asteroids. We have made great strides with our priority project building a 4-dimensional map of the solar system powered by broadly accessible, transparent, and open source computational tools to calculate and understand asteroid orbits. This space map will inform future services such as mission planning, asteroid visualizations, space navigation, and resource mapping. Thank you for tuning in to Asteroid Day and supporting the global space movement. We hope you are as inspired as we are by the stories pouring in from around the world.
In 2005, Congress directed NASA to implement a near-Earth asteroid survey program that would catalog 90% of potentially hazardous asteroids. These were defined as objects of 140 meters and larger, whose orbits bring them relatively close to the Earth. This act was signed into law by President Bush on December 30th, 2005. So let's break down 5 search facilities that are helping to achieve that goal. The major observatories, in no particular order, include the Catalina Sky Survey, the Zwicky Transient Factory, the Panoramic Survey Telescope and Rapid Response System, ATLAS, and the Verisi Rubin Observatory. Our third observatory is the Panoramic Survey Telescope and Rapid Response System, also known as PANSTARRS. PANSTARRS is a system for wide-field astronomical imaging developed and operated by the Institute for Astronomy at the University of Hawaii. Mostly funded by NASA and located near the summit of Haleakala on the island of Maui, PANSTARRS 2 telescopes have been extremely successful at finding near-Earth objects. Each telescope focuses on a separate patch of sky and then takes repeated images over the course of an hour. Anything that moves on those images is investigated further, as it could well be a near-Earth asteroid. The ATLAS system is a dedicated asteroid warning system that's being developed by the University of Hawaii, funded by NASA. It consists of 2 telescopes, 100 miles apart, which automatically scan the whole sky several times each night, looking for moving objects. Its name stands for Asteroid Terrestrial Impact Last Alert System, because if an asteroid were to completely escape detection until it's on final approach to collide with the Earth, ATLAS would likely be the system that sees it coming. So far, ATLAS has detected 594 near-Earth asteroids, of which 63 were considered potentially hazardous. Thankfully, none of these are known to be on collision courses with Earth. With an 8.4 meter diameter mirror, the Rubin Observatory will become an unparalleled discovery machine. Its 3.2 gigapixel camera will obtain images every 30 seconds, generating about 20 terabytes of data per night. That's equivalent to the entire congressional library every single night. Simulations demonstrate that during the telescope's 10-year survey mission, Rubin can be expected to discover and catalog 60 to 65% of potentially hazardous asteroids larger than 140 meters. This will bring the congressional goal for asteroid detection within reach, although the job will not be done. After that, astronomers will start the search for even smaller near-Earth asteroids. Observatory 2 is the Zwicky Transient Factory, ZTF. ZTF is dedicated to finding anything that changes in the night sky. It is a robotic surveyed camera located at Palomar Observatory near San Diego, California. On August 16, 2020, ZTF spotted an asteroid that had zipped past the Earth just a few hours earlier. With a diameter of just 3 to 6 meters, calculations showed that it was the closest known asteroid to fly by Earth without hitting our planet. It passed at an altitude of just under 3,000 kilometers, roughly 10 times closer to the planet than some communication satellites. The first observatory, the Catalina Sky Survey. Based at the University of Arizona's Lunar and Planetary Lab in Tucson, Arizona, the Catalina Sky Survey was originally commissioned to fulfill an earlier directive from Congress for NASA to search for asteroids 1 kilometer in diameter. Constantly upgraded and now supported by NASA's Planetary Defense Coordination Office, the PDCO, the Catalina Sky Survey discovered 1,548 near-Earth asteroids in 2020, setting a new record for the total number of near-Earth asteroids discovered in a calendar year by a single survey program. Together with other surveys, a total of 2,958 near-Earth asteroids were discovered in 2020.
It's so important to study asteroids because these fragments of rock are leftovers from the beginning of our solar system, and they contain details about the formation of our planet and other planets. And so that's extremely important to know how things got started. And the carbonaceous asteroids like Bennu that our satellite NASA OSIRIS-REx has visited may even contain molecular clues to show how life began on Earth. And that's some really cool stuff. And because asteroids orbit with these constantly evolving, orbits, it's important to study them to know if they're going to be coming to our home planet and can do what happened to the dinosaurs. And so all of these areas, it's critical that we study them today.
Welcome to Asteroid Day Live 2021 and the panel on keeping track of asteroids. I'm Lucy Green, and together with my panel of guests, we'll be talking about the latest work in this area. Now, this year, Asteroid Day Live is celebrating the 25th anniversary of the launch of the NEAR-Shoemaker spacecraft, which was the world's first dedicated asteroid mission. Now, a lot has changed in that quarter of a century. So back in 1996, the number of asteroids that we knew of was counted in the tens of thousands, whereas last year the International Astronomical Union's Minor Planet Center catalogued its 1 millionth asteroid. So how on earth do we keep track of all these objects? Well, to fill us in on what happens behind the scenes at the various space agencies, observatories, and other organizations around the world, I'm joined by an expert panel that includes Marco Micheli, who is a near-Earth object observer at the European Space Agency's NEO Coordination Center, Laura Fagioli, who is a near-Earth object dynamicist, also at the same ESA Center, Lynn Jones, who is a performance scientist at the Vera Rubin Observatory, and Ed Lu, who is an astronaut and also executive director of the Asteroid Institute. Now, Marco, I'd like to start with you because 1 million asteroids sounds like an awful lot. But how many more do we think are out there waiting to be discovered?
Well, there are a lot. It depends a bit on how big you count something to still be an asteroid. But 1 million is a large number, but we have to think, first of all, that the vast majority of them, I would say 97, 98% of them, of those we know, are in what we call the main belt. That is the belt of asteroids between the orbit of planet Mars and the orbit of Jupiter. So they stay there. They're cool to study, but they are not exactly what we are mostly interested in. Of those millions, so we have about 25,000 that we know of that are what we call near-Earth objects, NEOs. Those are the ones we care most about because they are the ones that can come close to the Earth, as the acronym itself says. How many of those do we know? Well, 25,000. How many of those do we think exist? A lot. And it depends again on the size. If we limit ourselves to things bigger than about 30 meters, which is what is capable of causing some pretty serious damage if it falls on the Earth, then there are about 1 million of those. And we only know a few thousand of them. So there's still a lot to discover. Of course, not all of them come close enough to actually pose a threat on the short term. But before we can actually evaluate if a specific object comes close enough to be a threat, we have to discover them. And that's why the projects like the ones we're working in exist, to keep track of them, discover them, and monitor them.
So I'd like to ask a bit more about then. So what kind of dedicated observatories or survey telescopes are being used to identify and track these objects?
Yes, there are basically two types of telescopes. The first one is what you mentioned, is the survey telescopes, and they are telescopes dedicated to discover an asteroid or astronomical objects in general. So they just scan the sky basically every night. They scan every part of the sky they can see, and they look for interesting things. In this particular case, they look for asteroids. They look for moving objects in the sky. Those survey telescopes then, when they detect something new, they check if it's new or if it's known, of course. They measure its position, what we call astrometry, that is the accurate measurement of where the object is in the sky. And then they report this position to the world so that other astronomers know they exist. Right now, there are a few operating surveys. Most of them are in the US right now, funded mostly by NASA. ESA, the European Space Agency, is also in the process of building its own survey telescope that will be installed in a few years in the south of Italy. After the discovery part is done and the knowledge of a new object being in a particular direction of the sky is sent out to the world, then there are other telescopes dedicated to what we call the follow-up, which is the targeted observing of a newly discovered asteroid over the days and weeks and months and years after the discovery, to make sure that we have the best possible data on the object and we don't lose the object, but we can actually monitor its motion in the sky. And again, other telescopes, typically slightly different, have this job to follow up.
And the European Space Agency recently deployed two 56-centimeter fully robotic telescopes as part of its space safety program. How did these robotic telescopes feed into the overall work that's being done?
Yeah, as I briefly mentioned, ESA is in the process of building a survey telescope called the FlyEye, which will be a pretty large 1-meter telescope dedicated to discovering incoming objects that are just about to come close to the Earth and possibly hit us. And in preparation for this, of course, there is a lot of technological development, including software and hardware and different things that have to be prepared. So ESA also built two smaller telescopes, 56 centimeters each, called the testbed telescopes. And they put one of them in Spain, one of them in Chile. And the idea is to do two different things. The first one is to test all the software and hardware machinery that goes around building the future FlyEye. And the second is actually to start playing a survey and a follow-up in these in-house built instruments, with distinct instruments, so that we can get the experience and get the confidence to be able to operate the FlyEye when the FlyEye is available. So these, of course, are available earlier, so we can already use them and we can already.
Well, Marco, thank you very much for that introduction. That really sort of sets off our panel well. But simply finding asteroids isn't enough. In order to not lose them, you have to calculate their orbits and, of course, keep track of them. And this is where Laura Fagioli comes in. So, Laura, welcome to the panel. Could you talk to us about what observations and data you need to calculate an asteroid's orbit so that you can then keep track of it?
Okay, well, astronomers, okay, actually we need only observations, and astronomers send object observation, that means object position at certain times, to the minor planet center, which is the center in charge to collect and disseminate those astrometric observations. And what do we do with this observation? Okay, well, we try to fit an orbit. That means we try to find an orbit which is compatible with the observation we received from astronomers. Of course, orbits we compute are not precise. That means there is always an uncertainty associated to them. But every time astronomers produce new observations for the same object, we have to recompute the orbit. And thanks to this new data, the uncertainty decreases, so that the orbit knowledge improves. Therefore, more observation we have, and arc in which we collect them is longer. So astronomers observe the object at different times for a long time span, more accurate will be the orbit. So it is the orbit determination process is an iterative process.
Right, so it's not just a case of making some observations and then you've got all the information you need.
No, exactly.
So I'm wondering, how quick is that process then? Do you need to get observations over days or weeks or months or even years to be able to get an orbital determination that is sort of sufficient?
Okay, the first time we just need 3 observations, so we can have observations from the same night. But as I said before, if we have more observation in a different time, so in a time span of days, weeks, years, is better, because in that way we can better know the orbit. So we can better know where is the object when we are interested into this object.
And then if you find an asteroid that is on an orbit that's going to bring it close to Earth, what happens then?
Together with the orbit determination, we also compute the closer approaches with the Earth. And of course, the impact monitoring process is triggered. What does it mean? We are again in the iterative process. So every time we receive new observations, and so that we can recompute the orbit, we also compute the impact probability. What is the impact probability? It's the probability of the object to hit the Earth in the next 100 years. If that probability is non-zero, the object is included in the so-called risk list, which is available at the NEOCC web portal. Of course, it is fundamental to follow up the more important objects included in this risk list, typically to lowering their impact probabilities, or better to rule out them from the risk list. So, okay, then when we know that an object can hit the Earth, the first thing to do is reobserve them.
once you've got your information about asteroids and they've been detected and you have got your impact probability, how do you then keep track of them afterwards?
The ball goes back to the astronomers again in this case, and to the people like me who not just keep track of surveys of discovery of new asteroids, but also of the follow-up. So the system that people like Laura operate, they provide us not just with the impact probabilities, as she said, but also with what we call an ephemeris, that is a position in the sky where the asteroid is. And so we, again, iteratively, as Laura said, we point at this part of the sky where we think the object is. And when we reobserve it, we remeasure it, we send the data back again to people like Laura, who recompute and produce a new ephemeris, so a new location in the sky where the object is. And this process goes on, astronomers observing, mathematicians predicting the position and giving us the new prediction so we can find the asteroid again over and over. And we repeat the cycle of computing, observing, and so on, over and over for many days, months, years, sometimes decades, until we either confirm that an impact is about to happen or we disprove all possibilities of impact.
Brilliant. I mean, I'm really getting a sense of how interconnected the global community is. And I think now is a really good time to move on to our next panelist, our next guest. Because when it comes to detecting asteroids, we've been hearing about these different observatories around the world, sort of growing that picture. But there's one that I want to bring in, and that is the Vera Rubin Observatory. And Lynn, this is your expert area. So maybe you could just sort of, first of all, briefly tell us about this observatory and what it's designed to do.
So the Verisi Rubin Observatory is a 6.5 meter diameter telescope with a really large field of view. So it's 9.6 square degrees field of view. This is a next generation survey telescope. The idea is we'll go with the telescope, survey the night sky, all of the sky that we can see, and do this every 3 nights, twice so that we do it 2 times a night and then come back every 3 nights or so. And just do that over and over again for 10 years. So this lets you build up a very deep image of the sky, which is nice for doing things like cosmology and measuring the shapes of galaxies, finding very faint stars. But it also lets you find all the transient objects. So this includes stars that explode, but it also includes asteroids, which are moving, so that this is how we can see that there are asteroids, and we can track them by going back and observing the sky over and over again. We get to get many, many observations of all the asteroids. And so we build up like this catalog of, it will have probably about 5 million main belt asteroids, somewhere between 100,000 and 250,000 near-Earth asteroids. And so there'll be all of these objects, including things from the outer parts of the solar system and comets. And from this, for each object, we get hundreds of observations. And so we not only can determine their orbits, but we can also do follow-up and figure out their colors, a little bit about their rotation properties. And so it's a really, really nice data set.
That's really interesting to hear, because I didn't really, prior to this conversation, associate the Verisi Rubin Observatory with even solar system objects. So I think you said you're aiming to, or you think 5 million asteroids might be discovered in this data set, and you'll be doing the science as well as providing information on the orbital movements as well. So do you think this data set has the potential to really be transformative in the area of asteroid research and asteroid tracking?
Yes, I do. The nice thing about the data set from Verisi Rubin is that for almost all populations, we'll have between 5 to 10 times more objects than we currently know, right? So we know about 1 million asteroids now. After the Verisi Rubin, after we execute the legacy survey of space and time, the LSST, we will have 5 million asteroids in that catalog. And so you might say, well, 1 million, 5 million, what did that help? But it lets you do things like split them up into finer sets. So there's these resonances in the main belt of the asteroids. And at the edges of the resonance, it gets very complicated dynamically. And so by finding many, many more objects, we can really map out what those resonances look like. And we can also do things like see what happens to asteroids after they collide and then their fragments are drifting apart through space, what we call these asteroid families, the collisional families. And so you can map out these collisional families to greater detail than we could before. Now, these are main belt asteroids, not so much the near-Earth asteroids. For the near-Earth asteroids, this is, again, sort of on the order of 10 times more objects. So you can do a lot more detailed analysis of different subsets of the objects.
Fantastic. It's so exciting to hear what's possible with this data set. And, you know, it's making me think about the volume of data that we're going to have in the coming years. And so I think, Ed, this really sort of nicely brings us into your area as well, because when we have all this data, we need to make sense of it, we need to analyze it, and we need a new, potentially, I would think, a new generation of software in order to be able to do this. So the question I want to ask you is, when did you sort of first realize about the enormity of the challenge of coping with this new flood of data? When did that become something you've been thinking about?
Well, we've known for years that the Vera Rubin Observatory is really going to revolutionize our knowledge of the near-Earth asteroids, the asteroids that come close to the Earth. As Lynn mentioned, we are going to discover somewhere around 10 times as many near-Earth asteroids as we currently know. And, you know, that process means that we're going to have at least, you know, for all of the asteroids which have a possibility of hitting the Earth, the ones that Laura mentioned, when you calculate their orbits, we know they're coming close to the Earth, we're going to be having 10 times more of those. So to give you an idea of what's going to happen here, we did look at just the discoveries in the first year of operation, and that's coming up in just 2 years. So when the Vera Rubin Observatory starts operations about 2 years from now, just in the first year, about 3 times a week, it's going to discover an asteroid that actually has an orbit that, if you look at Earth's orbit and the orbit of that asteroid, there is a possibility that they intersect. Now, 3 times a week is pretty often. Okay, it's quite a change from the way we operate today. And most of those asteroids obviously are not going to hit the Earth, but the process that Laura and Marco mentioned of additional observations will rule those out. But for some period of time, there are a lot of asteroids which have a possibility of hitting the Earth that we cannot rule out. Okay, so it's going to be a complicated situation here starting in just 2 years. So what we realized is that one of the important things we really need to do is get ahead on this data processing front, because there are so many observations. There's something like a petabyte of data, I believe, per night coming out of the Vera Rubin Observatory. And then when you process all that down, that's a lot of computing power. And so we're attacking this problem from the computational side. From how do we make sense of all these observations, and how do we best present this data in a way such that other observers around the world can do follow-ups, so that policymakers can look at these things and understand the importance of the various observations. You know, when I say importance, I mean things that might hit the Earth.
And you've spearheaded the development of, I think, a piece of software called ADAM to help with this analysis. Could you tell us what ADAM stands for, and what will the software do?
Yeah, ADAM is not really a piece of software. It's a software computing platform. What it is it stands for Asteroid Decision and Mapping Platform. What it really is if you think of what Google Earth is, or Google Maps, that's a platform that takes images, data, street level to satellite of the Earth, and turns it into something that people can use easily, right? When I want to drive from my house to someplace else, I don't want to call up satellite images and request data from satellites and look for road maps from the U.S. Geological Survey. I just want to say, how do I get from here to there, right? And what it has done is revolutionized the way people make sense of geographic data. Now, we're going to have a similar problem with the data of the solar system, the kind of data that's going to be coming out of the Vera Rubin Observatory and other large telescopes. And the question is, most of the scientists actually want to get to the information in it, not to how do I get hold of this image or that, or how do I bring in all the various sources of data. You just want a system that just sort of helps you organize that. And that's really what we're building for space.
So the software platform will be used by professional scientists. Have I understood that right? And when will it go online and be available?
Well, it's being used internally right now. Within, we're using it right now with our collaboration at the Asteroid Institute together with the Vera Rubin Observatory. We are beginning to open it up to other professional astronomers, but it's a development process, and we really have 2 years. The clock is ticking until the observatory goes live, so we have a lot of work to do.
Brilliant. Well, thank you very much, Ed. I mean, I think that was across the whole panel, just a really fantastic sort of overview of where we are, but also where we want to be. There's an enormous amount of work going on. And it seems really that, asteroid detection and tracking is almost sort of moving on to being an industrial scale endeavor. So both exciting, but also slightly daunting as well, with this 3 asteroids per week that could be near-Earth objects. So thank you again to my panel. Absolutely fascinating to hear your thoughts. And thank you so much for your time as well. Now, stay tuned to Asteroid Day Live. We've got a lot more coming up, including how we're getting to know the asteroids better than ever, how we're going to try and deflect an asteroid as a test, and what promise the asteroids may hold for our future exploration of the solar system. So don't go anywhere. And happy Asteroid Day.
So I was looking for a hobby during quarantine, lockdown, COVID times. I had just purchased this new telescope, and it felt like a really good social isolation activity, something that I can do at night with limited people, frankly, in my backyard. So I started using the telescope a fair amount. And I started looking at galaxies and nebulas. But it was really when I kind of found an online community of amateurs kind of like myself, where we were able to have targets, have missions, to have kind of a goal in what we were looking at. That's really when it became a true hobby. It became a hobby where there was a social connection, even if it was online, and we all had kind of a mission to look at the stars together. I guess what really drew me to continuing my astronomy journey and kind of learning about astronomy is really around kind of the data collection piece. It's always really nice to look at the stars and the galaxies out there, but being able to contribute to science, being able to collect data that really matters, that really goes into databases and that can theoretically help plan missions as probes get launched all the time. That's what really started intriguing me, I guess you can say. I would have various targets. So for example, I would have an asteroid would be passing in front of a star. And we would have our connected kind of distributed network of people all across the US and Europe and Japan point to that target if that path crossed over our heads. And using kind of the data and kind of triangulating, we could see the shape, the size, and start to define some of the characteristics of asteroids. And that's incredibly attractive to me, being able to contribute to the science in that way and actually being able to do it from my backyard. There's so much to discover still kind of out there, and telescopes, the professional telescopes can't point to everything all at once. So they use amateurs kind of like myself and other people that I've been interacting with to really start characterizing these asteroids. So this past weekend, I was able to join up with 5 other unistellar amateur astronomers as we kind of looked at a star. So At 1:34 a.m., I was in my backyard pointing towards a star in the sky, and I was able to watch as it briefly dimmed and kind of flickered out over the course of, I recorded for about 4 minutes. During that time, it flickered out for about 5 to 6 seconds. And that was kind of the occultation where an asteroid passed in front of a star. And this particular one was really interesting to the network because it actually links up to a NASA mission that's going to be launching, I believe in October of this year. The asteroid Patroclus is a target for NASA's Lucy mission. So being able to kind of help characterize, help define a little bit more, definitely contributes to the science. And it was very exciting to be able to be outside kind of in the middle of the night, really watching it flicker. You never know if you actually caught it or if it was your imagination a little bit. And then kind of the post-processing data and receiving a report that says, hey, you had a positive view. 3 other people in our network did, a few other networks also did, and we're going to combine it all together and have really cool information on this asteroid. That's contributing to science, and it doesn't take that much effort on my part.
Hello, my name is Carlo Thelen, and I'm the CEO of the Luxembourg Chamber of Commerce, welcoming you to the 2021 production of Asteroid Day Live. As a professional chamber and public institution encompassing all sectors of business in Luxembourg, one of our goals is to position Luxembourg as a hub for the growing space industry. Several major satellite operators have already been present in the country since the 80s. As you might know, SES was started in 1985 under the name Société Européenne des Satellites as the first private satellite operator in Europe. In 1988, the firm launched its first Astra satellite. Over the past years, the Luxembourg space sector has made great strides resulting from the strategic decision of the government to further develop and extend the space business economy. Luxembourg might be one of the smallest European states, with a population of over 625,000 people, but the Grand Duchy is reaching for the stars. In 2017, Luxembourg became the first European country and the second country worldwide, after the United States, to offer a legal framework. It secures property rights for space resources. Luxembourg is ready to join international efforts to harmonize global rules for peaceful exploration and utilization of space resources. The country aims at fostering collaboration between key players in the space industry in order to push technological boundaries and promote the development of policies and laws required for a sustainable space ecosystem. Luxembourg has also set up a space-oriented education. Our country offers a number of financial tools to space entrepreneurs either already based in Luxembourg or considering to move to the country. Space-related services and businesses have developed. Today, Luxembourg's space sector's contribution to the nation's GDP is amongst the highest in Europe. Numerous companies and players in the sector have launched businesses in Luxembourg. The country's space sector now consists of more than 50 companies and 2 public research organizations that cover various segments of the industry. So in 2017, when Asteroid Day was first invited to Luxembourg, we immediately wanted to take part in this successful global movement. We are extremely proud to be part of this 4th yearly event and to see interest for the space economy grow. We are delighted that the Asteroid Foundation, which is organizing the Worldwide Asteroid Day, chose Luxembourg for its headquarters. We hope you all enjoy this year's Asteroid Day Live. Thank you very much.